We're here at the construction site of the new I-5 Willamette River Bridge in Eugene, Springfield. Construction crews have been hard at it now since the groundbreaking in August of 2009. It is the largest bridge project in Oregon's bridge delivery program. The Willamette River Bridge is a vital link in the Interstate 5 system, a critical piece in the movement of people, goods, and services throughout Oregon, affecting the entire West Coast economy. The original freeway bridge, built in 1962, completed the construction of Interstate 5 in Oregon. Serving as a gateway for Eugene and Springfield, it was built as a concrete box girder bridge. Designed with a 40-year service life, the bridge began to show its age when ODOT inspectors discovered shear cracks in bridge girders, forcing weight limits to be imposed on the bridge, severely impacting freight traffic and forcing lengthy detours.
When we noticed the stress in the bridge, we were looking at what it might be able to handle as far as live loads or the trucks that might be on the bridge. And we quickly realized that it was going to be less than legal loads. The impact of having to detour or take loads off the interstate and detour them on other freeways, other local roads, was going to have a serious impact on not only the local economy, but the states and the west coast of the United States, because it is such a vital link in the economy of this area. So we immediately set off to build a detour structure so we could take traffic off the bridge and onto the detour structure and keep traffic flowing.
The new bridge needed to be capable of carrying the projected travel loads of the future and bringing a landmark design to the river communities of Eugene and Springfield. The Willamette River Bridge project is complicated. It is a very long interstate bridge built over a major local roadway, cutting across critical fish and wildlife habitat, active railroad tracks, and a park with busy pedestrian and bicycle commuter paths, all in cities known for a high degree of citizen involvement in the community decision process.
For a major bridge like this, it takes planning around the capacity it might have to have, the number of lanes on the bridge, the community involvement for aesthetics, as well as how we might handle live traffic. This bridge, the existing bridge, carries live interstate traffic that has tens of thousands of vehicles a day. And you have to prepare to deal with that traffic as you build the bridge. So along with those things, and then just the function of designing a bridge, it can take years to get ready to contract a bridge like this.
To accomplish the task of building a new interstate bridge over the Willamette River, ODOT is working with two Oregon firms, Obeck Consulting Engineers for design and Hamilton Construction for the demolition of the old bridge and the building of the new bridge, utilizing a new contracting method known as CMGC, or Construction Manager General Contractor.
Yes, we're using CMGC, and that's a unique contracting method where there is a triangle of support that builds that bridge, with the owner at the top or apex of the triangle, a design firm that designs the bridge, and a contractor that informs the design during the design process.
The advantages of CMGC are numerous and allow ODOT to work with the design and construction teams simultaneously and continually throughout the life of the project.
Well, I think there's been a huge benefit for this project that we're doing at CMGC. That being that the contractor has been at the table with us the entire time during the design phase. ODOT hired Hamilton as the CMGC pretty much the same time they hired us. They came on board about a month later, and they've been sitting at the table with us for all the design discussions, as well as reviewing our plans as we develop them. We've been having monthly over-the-shoulder reviews by the contractor where they get a current copy of our plans, they go through them, and they make comment of things we can change to make things more efficient, more constructible. And that collaboration, I think, has been greatly beneficial for a project of this size and this complexity. The other advantage that I see, I mean, you can get some of those benefits, and ODOT has done projects using design build, where the contractor and the engineer do work together as a team that the agency has hired. But that probably would not have worked very well for this project because there were so many unknowns that no contractor engineer team could have put together a proposal and a bid. And the big part of that has been the community piece, the design of all the features in the parks and underneath the bridge on the south bank. Would have been very difficult for a contractor to negotiate through or to even know what kind of a number to put to it cost-wise in a design build. Well, during the environmental assessment process, they had come up with bridge types that met the criteria that was developed during the NEPA phase. It basically required long span bridges due to the criteria of only having one pier in the water in the main channel of the river. The existing bridge and the detour bridge, as you know, have many supports in the river, and there was a desire both for recreational use and for environmental benefit to reduce that and only have one pier in the river. So that drove us to long span solutions for bridges, and quite honestly, the community input drove the decision towards an arch, something with curves. The community didn't want just a typical plain girder bridge like we see that we commonly build every day on the highway. And I think a big part of that is because the community uses the space underneath this bridge quite extensively on the bike paths, pedestrians, the parks, the recreational boaters, and everybody wanted something special.
Working over the Willamette River is just one of the many environmental challenges of building a bridge sandwiched between Alton Baker Park and the Willamette Natural Area, while maintaining freeway traffic and railroad freight volumes through the work area. The river is home to several endangered fish species, requiring the project team to come up with a unique way to mitigate impacts from necessary pile driving in the river.
To support the temporary bridges, it's necessary to drive temporary steel piles, and these would be pipe piles, into the river. Then each time a hammer blows and hits the piles, it creates a sound wave. And this sound wave propagates from the pile into the waterway. And unabated, that can have very negative impacts on the fish in the stream. And so to reduce those impacts, the contractor built a very innovative bubbleator, basically an air curtain of bubbles that would surround the piles that would reduce the noise impacts traveling further away from the pile. And that has been very effective.
The construction of the new Willamette River Bridge seems to contain every challenge possible for a major highway project. These include construction of coffer dams, drilled shafts and massive rebar cages, falsework towers for supporting the spandrels and curves of the arches, and tons of wood, steel, and concrete, all choreographed for delivery, construction, and placement. Kevin Parrish provides us some details of the construction.
Well, the arch, ideally, is we would pour an arch concurrently and or simultaneously, so we equally loaded with this. But in this case, we really couldn't do that, so we designed our falsework to be able to pour a section on that end of the arch, the north end of the arch, another section here on the south end. And today we're doing our first 28 foot or so in each of these arches. We'll come back, we'll pour another 50 or 60 feet on this side, then a little more over here, up until we're about finished and we have the arch closure pour, is what we call it, in the mid-span of the arch. That's about 4.5 feet of the arch that'll be left out. What that does, for an arch works through compression. Loads coming down on the top of the arch transfer the force down to the drilled shafts and shaft caps here at bent 3, and the same thing there at bent 2. So once we've completed the arch rib concrete, we'll place the spandrel columns, then we'll come back and jack the ribs apart, and that'll put a compressive force into the rib. It'll lift the rib off the falsework, and then we'll lock the rib in place. Then we'll monitor the arch rib, make sure we've got the proper geometry. Then we'll pour the final concrete in this closure pour. It'll be similar to a keystone. The Romans would put a keystone in, was the last stone put in the arch. This concrete would be the last concrete placed in the rib.
A project like the Willamette River Bridge has a lengthy list of processes required to make the leap from groundbreaking to ribbon cutting.
We're placing a class 6,000 concrete, half-inch aggregate. This is probably one of the toughest pours we're trying to make here, because this is where the arch is the steepest, most close to vertical. And as a consequence, our concrete has to be so fluid that it will flow through the re-steel in the reinforcing cage. This concrete has entrained air in it to protect against freeze thaw. It has, viscosity modifying admixture to help it flow better. We've got a different size aggregate than they have experience placing with this particular mix. And so we've got to make sure we get a good job securing this form, otherwise it will creep up. And all of a sudden our arch rib is, instead of being 7 feet wide and 5 feet tall, it's 7 feet wide and 7 feet tall, which is a problem.
Over the next few years, the construction and design teams will be working diligently to put this new bridge into place. It will be a showcase for travelers over the bridge or passing below on the river. Either way it is encountered, the new Willamette River Bridge will serve the entire West Coast into the next century.
Well, I guess for the local community, I think I'd like to express my appreciation for their involvement. Not only have they provided us good advice and counsel in the community advisory group, but we've had good involvement in the design enhancement team as well. They've been able to provide us input on how to leave the project site better than it was before we started.
For more information about the Willamette River Bridge and to follow its progress, go to willametteriverbridge.org.